Alright, in this video we're going to do Chapter 23, Inference about Means. Remember, when we're dealing with inference, we could be doing a confidence level, or we could be doing a test of significance. The definition of inference is making conclusions about a population from a statistic with a known degree of confidence. We will be estimating and testing a population mean. Before we've been doing population proportion, so now we're looking at means. We always list the standard deviation with the mean. Now, to remind you, the formula for standard deviation is the square root of the summation of your x value minus your mean quantity squared, all divided by n minus 1. So if we don't know the mean, we can't know the standard deviation. So we're going to be estimating two things: the mean, which is mu, and the standard deviation, which is sigma. What statistics do we use to estimate the mean and standard deviation? Well, we use the sample mean, which is x bar, and the sample standard deviation, which is s. And then the sampling distribution looks like a normal model with a mean of mu and a standard deviation of sigma divided by the square root of n. But we don't know mu and sigma, so instead we use x bar as the mean and the sample standard deviation divided by the square root of n for the standard deviation. When we do this, we can't use z-scores, so our new model is a t-distribution. It follows a t-model. This model is referred to as the student t-model. There's a family of distributions, so it's not just the one distribution that we've talked about in the past. It's very similar to a normal model, that its center is at 0, it's unimodal, it's symmetric, and it's a curve that never touches the axes. The model changes based on the sample size and degrees of freedom. Degrees of freedom is equal to your n minus 1, so your sample size minus 1. It's generally wider than a normal model, but the larger the sample size or degrees of freedom, the closer the student t model approaches the normal model. So if we look, here's a normal model. Here's a t distribution when n is 50. Here's a t distribution when n is 1,000. So if n was 100, it'd be somewhere in between. So it gets closer and closer to a normal model with more samples. So if we wanted to do a one sample t interval, the conditions we would check are randomization. The population has to be greater than or equal to 10 times the sample, and it has to be a normal population, or n has to be greater than or equal to 30. So when we're checking condition number 3, the normality, it either has to be stated that it's a normal population, or if we have the data, we can look at a histogram of the sample values, and we want to see a normal shape. If we have the data values, we could also look at a normal probability plot. And remember, with a normal probability plot, you want to see a straight line when it's normal. Or if the sample size is greater than 30, then the central limit theorem kicks in and we can say that it's normal. Once the conditions have been met, we're going to use a t-distribution, not a normal model, a t-distribution, and we're going to do a one sample t-test or t-interval. Then we can do our mechanics. So we're going to either calculate or be given x bar, s, the sample standard deviation, and n, the sample size. We're going to find the degrees of freedom by taking the sample size and subtracting 1. We're going to find that critical value, which in this case is t star, which is we can either do by using inverse t on the calculator, or we can use table B, which is on a separate sheet. And then we're going to calculate the interval. So the formula is the same. It's your statistic plus or minus your critical value times the standard deviation of the statistic. But each piece is a little different. So the statistic is your x bar, your mean, plus or minus. Your critical value is t star. And the standard deviation, when I'm working with means, is sigma divided by the square root of n. We don't know sigma, so we would use s there. And that'll give us our interval. Then we could state our conclusion. So it would be, we are blank % confident that the true mean of, in context, whatever it is you're talking about, is between blank and blank, whatever units you're talking about. Now, for the calculator, to get your answer, you're either going to be given a list of data values, so you'll put all those data values into list 1, or you'll be given the x-bar and the sample standard deviation. So you're going to press stat, then you're going to press test, then you're going to press t-interval. If you have the data in a list, then you're going to use data, because you have two different options. You have either data or stats. If you were given x-bar and s, you would click on stats, and then you would put that information in. If you are doing the interval with the data, once you press t-interval, that will give you x-bar, it'll give you s, and it will give you your interval values. Alright, in our first example, it says a coffee vending machine dispenses coffee into a paper cup. You're supposed to get 10 ounces of coffee, but the amounts vary slightly from cup to cup. Below are the amounts measured in a random sample of 20 cups. Is there evidence that the machine is shortchanging customers? Construct a 95% confidence interval. So they gave us all the data values. So I would go into my calculator, I would go to list 1, I would put all 20 data values in. Then I could get all the information I need. I could get my x-bar, my mean, my standard deviation from that sample. So I would have n is 20, x-bar is 9.845 ounces, my standard deviation is 0.1986 ounces, and my degrees of freedom is 19 because it's 20 minus 1. So once I did all that, I have all those values. Now I can check my conditions. So they stated that it was a random sample. We assume that the machine makes more than 2,000 cups of coffee, so that's 10 times, or it really should just be 200, right? 10 times my sample. And then a normal probability model. So if I made a normal probability plot, I would see that it's approximately linear. So I drew a quick little sketch of the normal probability plot. And then I can say that the normal population is assumed. Remember, to make your normal probability plot, you have all the data in your list 1. So all you have to do is go to stat plots, turn one of your plots on, and then pick the type that's all the way over to the right side that looks like just a squiggly line, and that will make your normal probability plot. Make sure if you're using that method, you draw a quick sketch of a normal probability plot. Now I'm going to do an interval, so my process is x-bar plus or minus t star times s over the square root of n. So x-bar is 9.845 plus or minus. T star, I'm going to do inverse t, so I'm going to go second vars, that will bring me to my distributions. I'm going to go to inverse t. It's going to ask for area. So the area I'm going to put in is 0.025 because I'm doing a 95% confidence. So that means I have 2.5% on both sides. And then they're going to ask for the degrees of freedom, which is 19. And you'd get, it's going to give you a negative. We're just going to ignore the negative. So it's 2.093 is my t star value. Or you can look at table B. And then my standard deviation was 0.1986 divided by n, which is 20, the square root of n. When I do this, I get this value. If I use my calculator and just did the test, and then I would get this value. So it's pretty similar. And we could state our conclusion. So we are 95% confident that the true average amount of coffee dispensed is between 9.752 ounces and 9.938 ounces. Alright, so in that first example, for all the calculator pieces, I have all my data values in list 1. So I can go to stat, calc, one variable statistics. I'm using list 1, have it calculate. So that will give me my x bar, my standard deviation, the n value. It'll give me a bunch of other pieces, but those are really the ones that I need. Okay, so those are 3 key pieces of information that I need. Then I can do, to find my t star value, I'm going to go to second and then var, so my distributions. I'm going to go to 4, which is t, or inverse t. The area I'm going to put in is 2.5%, so 0.025, because I'm assuming I'm a 95%, so that means I have 5% left, which means I have 2.5% on either side. So the area is only on one side. My degrees of freedom is 19 because my n value was 20. So it's always n minus 1. If I put that in, I get my t star value of 2.093. Just ignore the negative. It's just because it's a left side tail. And then if I want to get my interval, I can do this all on my calculator. So I'm going to go to stat. I'm going to go to test. I'm going to go to t interval, which is number 8. I'm going to use data because it's all data that I have in list 1. Frequency 1. My confidence level is 95%. Calculate. And it gives me my values and all the pieces of information that I need. Pretty cool. Alright, the first set of your turn problems is page 555, number 13 and 36. We'll try those in class. Now, if we want to do a one sample t-test, it's going to be very similar to a z-test, a one proportion z-test. My hypothesis is going to use the mean, so mu. So my null hypothesis is mu is equal to whatever value I was given or I calculated for x bar. My alternative hypothesis is going to be that mu is either less than, greater than, or not equal to that same value. The conditions, it's going to be the same conditions I used for a t interval. So it has to be random, it has to be greater than 10% of the population, and it has to be a normal model. The conditions are met, we're going to do a t distribution, and it's going to be a one sample t test. Make sure you don't forget to state what it is that you're doing. The mechanics, we're going to calculate or be given x bar, s, and n. So we put all the data in. We do stat, calc, one variable statistics. We get all of that information. We're going to find degrees of freedom by subtracting 1 from my sample size. Then the formula, remember this is all, you can get all this information for the formula on your reference sheet. You just have to know how to read the reference sheet. T equals your statistic minus your parameter divided by the standard deviation of the statistic, so your standard error. So it's x bar minus mu divided by s over the square root of n. Our p-value is p is either going to be greater than or less than our test statistic, whatever we get for t. And then remember, if we're doing a not equal to, we have to do 2 times that probability. For our conclusion, we're going to compare our p-value to our alpha. It's going to be the same 2 sentences that we're used to, so we're going to state our conclusion in context. So it's either we reject or we fail to reject the null hypothesis because the p-value of blank is either greater than or less than the alpha of blank. So if your p-value is less than alpha, you reject. If your p-value is greater than alpha, you fail to reject. We have sufficient or insufficient evidence that the true mean of whatever it is you're talking about is either we write our alternative hypothesis there. Then to do the mechanics, it's all done in your calculator. So you're going to press stat, test, then you're going to go to t-test. If you have all the data in a list, you're going to click data. Then you're going to tell it to use list 1. You're going to put in whatever your mean is. You're going to see tell it if it's a two-tailed test, if it's a less than or greater than. Then you're going to have it calculate. If you have the stats, if you have the x bar and the standard deviation, you'd go to stats and you'd plug all that information in and then press calculate. Alright, this example, it says the EPA wants to show that the mean carbon monoxide level of air pollution is higher than 4.9? Does a random sample of 50 readings with a sample mean of 5.1 and a sample standard deviation of 1.17 present sufficient evidence at the 5% level of significance to support the EPA's claim? Previous studies have indicated that such readings have an approximately normal distribution. So I want to state my null and alternative hypothesis. Well, they want me to see if it's higher than 4.9. So my null hypothesis is that my mean is equal to 4.9, and my alternative is that my mean is greater than 4.9. Now I need all that critical information, so I'm going to write all the pieces of information that I know. Well, I know that mu is 4.9. I know that x bar is 5.1, the sample mean. I know that the sample standard deviation is 1.17. I know that n was 50, there was 50 random samples. Degrees of freedom is 49. And my alpha is 5%, so 0.05. Now I can check my conditions. So it stated that it was a random sample. The population is greater than 10 times n. We assume that they do more than 500 readings. And that it was stated a normal distribution. Also, n equals 50, which is greater than 30. So we can say that we're using a t distribution and we're doing a one sample t test. Alright, so here's the equation. So t equals our x bar minus our mean, our mu. So 5.1 minus 4.9 divided by s divided by the square root of n. So 1.17 divided by the square root of 50. If I plug that in, I get 1.2087. Okay, you could do all of this in your calculator, which is fine, but if you're going to do it all in your calculator, you still have to have some work shown, which means you still have to have at least the formula written. So be very careful that you don't just go, okay, my answer is 1.2087, and then my p-value is this. So my p-value, t is greater than 1.2087. So p is 0.1163. Since our p-value is larger than our alpha value, we fail to reject the null hypothesis because our p-value of 0.1163 is greater than our alpha of 0.05. We have insufficient evidence that the true average of air pollution is greater than 4.9 units. A test, a t-test. So a t-test is number 2. They gave us stats, not data. So I would put in for my null hypothesis, it was 4.9. For x bar, I had 5.1. For my standard deviation, I had 1.17. N was 50. I was doing a greater than. And calculate. So it gives me my t value. It gives you my p value. Gives me some other information. So my p value matches what I get, but make sure you always write the formula. It's very important that you still have that formula there or you won't get full credit. Alright, and your turn problems are page 557, number 33, and 34. And we'll do those in class as well.